Hi, so I hope I'm audible to you.
Yeah, I can hear you.
Okay, sure, thank you. So, before we begin with today's session, let me just ask, do you have any doubts from the previous class? Either of the previous assignments that we had discussed earlier?
No, no.
Okay, so that's fine then. I'll just start discussing the assignment of today's, the third one. Okay, let me just start it formally. So hi everyone, good evening, welcome to tutorial 3 of the NPTEL course on nonlinear and adaptive control. And I'm Anchita Dey, I'll be the PMRF TA for this course. I'm a PhD student working with Professor Shubhendu Vaseem at IIT Delhi. So let me start sharing the screen, and today we will be talking about, briefly discussing about assignment 3. Um, so is the screen visible? Can you see the OneNote?
Yeah.
Okay, sure. Thank you. Okay, so I think this session for this week, sir had mainly discussed about MRAC first, and then he moved on to talking about adaptive command tracking, and then how can we actually robustify these methods. So the robust adaptive control part has just started, and this would go on for, I think, one more lecture in this week. So the first assignment uh, talks to us about these four options, that robust adaptive control. Let me just, yeah. So robust adaptive control is used to handle which of this? So I think it's a very easy question, but to give it away, we have two words here, robust and adaptive. So the adaptive means that if you don't know something, you would be able to handle it. And what's robust? Robust says that, well, if there are any disturbances or uncertainties, owing to which you might not be able to learn or design a suitable controller using the usual MRAC methods or the standard simple methods that were taught in the class till now. In that case, we robustify the law. So, like for example, one of the answers is of course very clear. You can handle unstructured uncertainties, right? So something that you don't know is like giving, say, let me see if I can write it quickly. I can just say it also, like if you have xt dot is equal to axt plus but, and then you have say plus dt in that expression. Yeah. So suppose you have something like x dot, I don't know, yeah, is equal to ax plus bu plus d, right? So here, in fact, what is this d thing? It's simply saying that you might not know what lies inside the d structure. For example, your input, it might have a disturbance, like say x dot is equal to ax plus bu plus say sine of t plus cos of t. Now in this model, this is a part which was inbuilt inside the model, and when you were trying to identify the system model or come up with a model for the system, identification means to learn about the system dynamic parameters. So when you try to do this, it's possible that you might not know what structure lies inside D, but you have some idea. For example, if it's sine t plus cos t, then it would always lie between a range, right? Because sine t is between -1 to 1 plus cos t is between -1 to 1. So at max, they can be between -2 and 2. So you can say in this case that the norm of D is less than equal to 2, right? So that's the range in which D would be oscillating. Kind of in this case, it would oscillate, but it doesn't have to be a sin t plus cos t kind of signal. It can be anything. So such cases are called the unstructured uncertainties, provided you do not know what the structure is. That means this sin t and cos t part, this was hidden. Okay. Yeah, I think this is better. So for example, yeah, like this is one of the obvious answers. So robust adaptive control can be used to handle unstructured uncertainties. Now, what about unmodeled dynamics? If you have some, it's a similar case. If you have some dynamics, but it's unmodeled, that means you don't know what form it has. So you just simply write it as something, say some, some alpha of x comma u. That means you know this is some portion in the dynamics which depends on the state and the input, but you do not know what exactly its structure is, or you were not able to model it. So that kind of thing can also be handled using robust adaptive control. What about external disturbances? Of course, external disturbance, that's the easiest way, right? So I think in class sir has talked about dead zone and I don't know if you went to sigma mod and E mod or not, but dead zone was discussed, and that was one of the like easiest ways to deal with external disturbances, okay, or additive disturbances also. We also call them to be additive bounded disturbances. They might be additive unbounded as well, but the catch is that for dead zone modification, you need to know the bound, right? So these were some of the examples, and then it's kind of clear that all three options are working. So you can handle each of these three using robust adaptive control. Okay. Is there any doubt?
It is understood.
Okay. Okay. So we can then move on to the next question. Yeah. So yes, we already talked about Z dead zone in a brief way. And which of the following statements are not true about dead zone modification? So the first point that has to be noted is that you have to say what is not true, right? And then what is dead zone modification? So it's simply a robust modification of already existing the adaptive laws. For example, if you have an MRAC designed, you can modify it using a dead zone modification, right? So the next question turns out to be that what was the motivation for robustifying the adaptive laws? There were certain motivations that sir had discussed in the class, right? For example, you would want to prevent parameter drift. You would want to handle any additive disturbances. You would want to handle any parametric uncertainties, right? So that means it can prevent parameter drift, which is true. That's one of the correct options. It can improve the system performance, of course, because suppose in a simple way speaking, say you are given a system x dot equal to ax plus bu, and there is some disturbance d, right? You can just consider the previous example that we talked about. Now, if you do not know d and you simply design a controller for x dot equal to ax plus bu, it is very possible that the performance would be bad because there is a constant disturbance working as an input to the system, right? So it turns out that if you are robustifying your adaptive law, if you're robustifying the controller basically, then of course the system performance would be better because you have addressed the uncertainties or have addressed the disturbances that were present in the model, right? So it would improve the system performance. Right? And then these two are very specific to dead zone modification. So knowledge of the upper bound of the disturbance is required actually when you do a dead zone modification for any given adaptive law. But knowledge of the structure of the disturbance is required or not? Well, that's not the case. So you don't need that. You just need to know the upper bound. And with that, because that's how the dead zone works, right? The dead zone is basically saying that suppose the uncertainty bound crosses this region, then you will change the adaptive law. And if it is below this region, then you will let the adaptive law be of a different structure. So there is a dead zone, a zone in which the law is not being activated, right? So that means you don't need to know the structure. All you need is the upper bound. So it turns out that 3 of these statements are true about dead zone modification. So you have to find out which one is not true, right? So I think that's yeah, that's all for this question. I didn't have much to say. So I will still advise that before you solve this question, you just go through dead zone modification once, which would be the initial part of Hauser discusses about robustifying the adaptive loss. This question is also very easy. So I think I might skip it as well, because which of the following structure of the modeling uncertainty can be handled by MRAC? Now, there's a particular type, and this is a very simple theoretical question. So, of course, nonlinear in parameter are not the options. You have to just find which ones out of the LIP or linear in parameter, whether it's the matched one or the unmatched one. Right? That's your task to do to solve the assignment. Yeah, so now we can go through this very question. If A is Hurwitz, then which of these options would be correct? So what is meant by the term Hurwitz? Simply says that yeah, A is Hurwitz means that so the basic thing I would like to say is that the word Hurwitz is used when we are dealing with the continuous time systems, and in continuous time case, this simply means that the eigenvalues of A are negative, or that means they would be in the left half of S plane. The roots would be in the, so I should not have written in the left half of S plane. So eigenvalues of A are negative. That is, you can say that the roots of the characteristic equation obtained with lambda I minus a, and then you take its determinant and equate it to 0. This would turn out to be a negative, or you can also say that the poles are in the poles of the if you write the transfer function, poles of the transfer function, there is a slight lag, I think, again. Yeah, so the poles of the transfer function that you can form with the given A matrix, that would be in the left half of the S plane. Okay, so that's what we mean when we say that A is Hurwitz. And in fact, just to add this for your knowledge, like if you are dealing with discrete time systems, in fact, instead of the continuous time ones, for example, then you will have your system written in the form of xt plus 1 equal to axt plus a but. You can notice that we do not have any x dot kind of term here, right? The x dot term here. Why? Because this is in discrete setting. So in discrete mode, you just have different values of x at different time instance. You do not have any, since there is no continuity, you can't do any differentiation basically. So in this case, it's for the discrete case only. So okay, I need to give a permission. Just a minute. How this works. I will maybe keep it open. This would be the best thing to do. Right. So for discrete, instead of this Hurwitz thing, we just say that A is Schur stable. Okay. So Schur stable means the same thing except that now you are in discrete. So um, if you recall, when we do the analysis in discrete time setting, we have this notion of going to the Z domain instead of the S domain, right? And in Z domain, we say everything inside the unit circle, or all the poles lying inside the unit circle lead to a stable system. That means now you would want your eigenvalues to be between the modulus of it to be less than 1. That means they would be between -1 to 1, which is the unit circle. Okay. So anyways, that was a side uh, tip just for this question. So in case of the continuous time system, we will be analyzing this. For discrete also you can do similar analysis. Okay. So if A is Hurwitz, then which of these options would be correct? Right. So what is this? This PA transpose plus AP, or PA plus A transpose P. Whichever you pick, it kind of seems like this is a structure which is equal to a negative sum matrix, right? This is equal to, in each of these options, you can see that Q is equal to Q transpose, which means Q is symmetric. P is equal to P transpose, which means P is also symmetric. And in fact, these are either positive definite or positive semi-definite, right? So if Q is either a positive definite or positive semi-definite, it just means that minus of Q would be negative definite or negative semi-definite. And where exactly do we deal with this, this notion of something is positive definite, and then we go for something that is negative definite or negative semi-definite, right? So the answer is in case of the Lyapunov analysis, right? So this is what we are going to do. We will just start with this x dot is equal to ax, and with just a minute. Yep. So with x dot is equal to ax, we simply consider a Lyapunov function. Let this be equal to x transpose px. Okay. Then our v dot is equal to x dot transpose px plus x transpose p x dot. So you just take derivative of this term first, and then you take derivative of the second one, right? So then this is equal to, you just replace the expression of x dot, which was ax, and you put it here. You get x transpose A transpose px plus x transpose and then p ax, right? And then if you take x transpose x common in both sides, you kind of get a matrix which is pa plus A transpose p. Now if this is my v dot, I would want this to be negative definite or negative semi-definite, right? So the question said that A was Hurwitz. That means the performance would lead to all the poles being on the left half plane, which means it would be converging to 0. So it would preferably be going for less than, right? It won't be a negative semi-definite, it would be a negative definite. If it was negative semi-definite, that means one of the eigenvalues would be equal to 0, or there would be a complex conjugate pair lying on the imaginary axis. All those situations would appear, which is not the case. It's straightforward said that A is Hurwitz. That means this should be negative definite, and if this is negative definite, that means PA plus A transpose P. So if we just write it, we have PA plus A transpose P, which is equal to minus Q, right? Let me just say that, well, this is equal to minus X transpose QX with Q being greater than 0 and Q is equal to Q transpose. That therefore, that is P is positive definite and Q is also positive definite, right? And then the analysis would lead you to, you can see, I think, the options. whichever are given here. So you have PA plus A transpose P to be equal to minus Q, right? So at least the sequence is clear where the transpose would be, and then you can choose which one you want to get to ensure that A means to imply that A is Hurwitz. Okay, and I think you can quickly remove some of the options with less greater than equal to, because whenever you choose a Lyapunov function, the candidate function is always chosen to be a positive definite function. We don't start with something that is positive semi-definite, right? So that kind of gives away the answer to this question very easily instead of going through all the rigorous analysis. Okay, so we will now move on to the next question. Okay, so the next question says, consider the plant x dot is equal to ax plus u plus d, where d is a bounded disturbance and a is an unknown parameter, right? So it's kind of similar to the first example that we gave, and then if d is a bounded disturbance, we can just write, we can just kind of robustify the adaptive law. And then a is an unknown parameter. That means you do not have any idea about a, nothing. You don't know even the bounds or any specific structure of a either. But for sure that you see in this case, we can kind of assume that a is a constant instead of a time varying signal. So which of the following controllers u of t would guarantee boundedness of all the signals and convergence of xt to 0? Okay, so this very part is important. We want xt to be going towards 0, and if we are going to ensure boundedness, so we'll just be kind of trying with all the options. Okay, so the first thing that we notice is that while u is equal to minus kx is given for all the options, right? So it's quite straightforward that you would be implementing u. You would be implementing u, and that would do the job. So you place x dot equal to ax plus u plus d. There's too much background noise. Let me just. Yeah, sorry for the disturbance. So yeah, we were dealing with too many disturbances. That's the irony, I think. Okay, so we have u equal to minus kx for all the inputs, and so we will just first of all we will place it in the given system dynamics, right? We have x dot is equal to ax plus u plus d. If we put minus kx here, we get x dot equal to ax minus kx plus d, and then you take x common, so you have a minus k into x and then plus d, right? So there are some options, right? In some of the options you have the disturbance considered to be equal to 0. In some of the options the d is not equal to 0 but is some bounded disturbance signal. So in which case will you be applying which controller? That's the question, to ensure that xt is going to 0. So let us first consider a Lyapunov function v, and since we have to design a law for k as well, if you can see here we have k dot equal to something. That means you are designing how k is going to vary. So let's say that Let's say that v is equal to half x square plus half k square. Why k square? Because like I said, there is something involving k dot, that means k is varying with time. So therefore v dot is equal to half 2x into x dot, and then plus half 2k into k dot, and then you can just cancel these 2's, so you're left with x dot plus k dot. Now what we do is we substitute the expressions of x dot and k dot is well not known to us yet, and we'll be designing that. So we'll just substitute the expression of x dot, and we get x into a minus kx plus x into d. So this part is only whatever has been substituted from the dynamics, right? And then you have plus k dot, and which is equal to a minus k into x square plus dx plus k dot. Now the question is, what do we want from v dot, right? We just want v dot to be at least negative semi-definite. If it's negative definite, that's even better for us. So we will see what we can obtain by checking all of the options. Well, please, you can just note down the expression, which is v dot equal to a minus k into x square plus dx plus k dot. So what was the first option? Let's go back. It is k dot is equal to x square when d is equal to 0, k dot is equal to x when d equal to 0, right? K dot is equal to x square and when d not equal to 0, and then k dot equal to x. Basically k dot is given to be x square or x, and d is considered to be 0 or non-zero. So with the first one, we have k dot to be x square and d to be equal to 0, and then if you replace it here, of course this d term will not be present, and you are left with a minus kx square plus k. In place of k dot you put x square, so you have plus kx square. So again this kx square are getting cancelled, this two. So this one and this one would be gone, and you are left with ax square. So now the question is, what can you conclude? First of all, see, v was a function of x and k, right? Now the moment that the k is not present in the expression of v dot, it means that there is no chance of any definiteness. You can only get some semi-definiteness, right? And of course I'm not talking about the indefinite condition. Now what is a? We have no idea about a, right? That was given to us, that a is an unknown parameter. So you do not know. A might be positive, a might be negative. If it's negative, that's really good. We can have a negative semi-definite case for v dot. But if it's positive, then of course it's doomed to be unbounded, right? We won't get any bounded expressions, neither would x be converging to 0. So basically this case is not viable anymore. It's not a viable option at all. Let's now see for the next case. We have k dot equal to x and d to be equal to 0. Now if you place the same thing here, we have v dot to be a minus kx square plus kx instead of k. Earlier we had this kx square thing here, right? So that means now you can't even cancel anything, and you still have no idea about what a is. So basically you do not know what the structure of v dot is, whether it's going to be negative or negative semi-definite or negative definite. So this is like even a worst scenario to do any analysis. Right. Now we move on to the next option. We have k dot equal to x square. That's very good. But now d is not equal to 0. So then your v dot is equal to ax square plus see the dx would still be there, because you had some minus kx square plus kx square term, which both get cancelled, and you are left with only this. And again, you know that there is a bound on d, so might be if a was less than d, in that case you would have been able to, or if a plus d was something negative, you would have been able to comment something about v dot, but you have no idea about a, right? So you can do nothing. And then if we go for the last option, we have k dot equal to x, d not equal to 0, and c is again a very bad scenario. You have no idea of what v dot is going to be. So that means the first Lyapunov function that we chose gave us basically no idea about the analysis part or what we can do. So an alternative is that let's try with some other Lyapunov function, and why not consider something like, because we have this a minus k kind of term here, and we would want to do something so that the a term gets cancelled, right? Because in each of these cases, you see there is an a appearing in every scenario, right? And the problem was basically that you had no idea about it. So now in order to cancel this a minus k kind of thing, sorry, we try with a different Lyapunov candidate function. We say that let v be equal to half x square plus half now k minus a square. You can start with a minus k as well and see what comes up. So since I've already tried it and this k minus a thing works easily, you can also do with a minus k. So then your v dot would be x into x dot plus k minus a into, so k dot, right? And here this minus a dot term is becoming 0 because we assume that a is a constant. Since nothing was mentioned in the question to you whether it was time varying or not, you can assume it to be constant. And then it's given that with this very condition, we'll just be replacing the dynamics, whichever was given to us. So we have x into a minus kx plus x into d, right? And then we have k dot minus a k dot. Now if we expand it, we just get ax square minus kx square, yeah, plus xt plus k into k dot minus a into k dot, right? Now for this v dot expression, let's see what we can do. There is a chance that you can see there is a here with x square and k with x square. And similarly, we again have a k dot and then minus a k dot, right? So it seems like there is a chance to handle this unknown parameter a in a certain way. So we will just, we just consider when d is not equal to 0. In this case, you see v dot is equal to ax square minus kx square plus this xt term will of course stay here, right? And if we just take this common, we have a minus k into x square minus a minus k into k dot plus xt. Okay, now see, one thing is that x is available to us, right? So maybe we can do something with k dot and x such that these terms are getting cancelled. So we have k dot to be equal to x or k dot to be equal to x square. Those were the two options given to us for the case of d not equal to 0. And therefore k dot equal to x square would give us simply v dot to be equal to a minus kx square minus a minus kx square again in place of this k dot and plus xt. So we will simply be cancelling these terms, right? And we are left with the term xt here. Now the question is, do we know what d is? We have no idea. If d was equal to say minus x, that would have been really great for us, because in that case v dot would be negative semi-definite. But we have no idea in particular. So let us just leave this option for now, because this is not a sure shot controller that would make x go to 0. Now what about k dot equal to x? You can try and find out that the expression of v dot looks like this, again with not much to comment on. But if we have d equal to 0, right, in that case your v dot, in that case your v dot becomes a minus kx square minus a minus k dot, and because d is no longer here, so now if you put k dot equal to x, of course it makes not much of any sense because you have x square minus x here. But if you put k dot equal to x square, then your v dot turns out to be, I can just write it if I want, then your v dot becomes a minus k x square minus a minus k x square, right? And basically this is equal to 0. So you get a negative definiteness condition, and therefore k dot equal to x square with d equal to 0 is a suitable law, or is a suitable adaptation law. Where was the question? Yeah, is a suitable adaptation law for to guarantee boundedness of all these signals and convergence of xt to 0. Okay. You can in fact continue with Lassalle's invariance principle and do the remaining proof, but I will leave it up to here. So I think, yeah, those were the first 5 questions. So if there is any doubt, you can ask, or I will just move on to the next part. Okay, so we will move on to the next part. Yes. So we have 5 more questions left, and let's see the first one out of that. Let us consider a first order system as x dot equal to minus x plus ax plus bu, and x of 0 is equal to 0. That means the initial value of x at time t equal to 0 is given to be 0. So if the state x can be written as x is equal to theta transpose phi, yeah. So if the state x can be written as x equal to theta transpose phi, which is basically a linear regressor kind of form, then where theta is an unknown parameter vector and phi is a known signal vector, then which of the following represents the correct choice of theta and phi, so that you can write x to be equal to this, this theta transpose phi. We have some options given here, and you can see the very first hint that you get is that you have an s here. That means we have something to do with a Laplace domain analysis. We'll do some Laplace transform and come up with an expression for x which would look similar to x is equal to theta transpose phi. Okay. So yeah, given x dot is equal to minus x plus ax plus bu, and your x of 0 is equal to 0. Now it is said that it is possible to express x as theta transpose phi. This is unknown and phi is known. Now theta is a parameter vector. This is given to us, right? And then the question is, what parameters do we have in the given dynamics? If we look into the system dynamics, what are the parameters? The parameters are here a and b. That means if theta is an unknown parameter vector, it would have to do something with a and b, that it would look like a vector. It would be a vector which is comprised of the parameters a and b basically. So therefore theta will be made of ab, and then phi is a known signal vector, right? This was given in the question as well. Phi is a known signal vector. So if phi is a known signal vector, what are the signals that are given to us? You can see you have x here and u here, and that's it. You have the state and the input. So then phi would be made up of what? It would be made up of something of x and u, right? Either of this or both of this, or maybe some combination of these terms. So we will start with the analysis. We have been given x dot equal to minus x plus ax plus bu. Now if you take the Laplace transform, on both sides you have sx of s minus x0. We can also write x at 0 minus, that means the value just at the initial time instant. This is equal to minus xs plus a into x of s and then plus b into u of s, right? This you can see this very signals with bracket s, these are in the Laplace domain or in the s domain, sorry. So if we take this common, we have s plus 1 into xs, and this term is actually turning out to be 0. So this is 0 because it was given to us in the question. So we have, we do a simple side change, bring it here, and we have s plus 1 into x of s, which is equal to ax of s plus bu of s. So this simply implies that if you bring s plus 1 to this side in the denominator, we have x of s equal to a by s plus 1 xs plus b by s plus 1 us, right? Now we can see that it is somehow similar to whatever expression was given to us. We have this 1 by s plus 1 thing here as well, right? So at least we are close by. The s minus 1 expressions, you can simply discard them easily. Now with the s plus 1s, if you kind of take this common, you have a and b written in this form. So this is basically a into xs by s plus 1 plus b into us by s plus 1. Or you can in fact say that instead of writing in this row vector form, you can write it as a column vector and give a transpose here. So a b transpose and then xs by s plus 1, and here you have us by s plus 1. And if you recall, in the question we were given that x can be written in the form of theta transpose phi. So if you can write it in the form of theta transpose phi is kind of clear to us now. I hope that this, yeah, okay, it looks very bad. So this here, just a minute, it's getting erased every time I write it. This very term without the transpose part, this is your theta, and then whatever you have here, yeah, this would be your phi, right? So this is your theta and this is your phi. So then you can accordingly do the remaining thing to see which one would be the solution. Okay. I hope this was clear. Okay. So we will move on to the next question. We are given that consider a first order plant in S domain as x is equal to b by s minus 2 into u, and a reference model given by xm to be equal to 2 by s plus 1 into r, where here x is your state, u is your control input, b is an unknown constant, right? And so this b is the parameter that we do not have any idea about. Xm is the desired state that you would like for the for your given state x to follow, or a model state, and rt is a bounded reference signal. So this is also your reference signal that you is the reference the signal that you want your state x to be implementing in such a way. That means the controller should implement the R and include it in its design in such a way that X is following XM, or X is basically tracking XM. So for R is equal to 2, which of the following indirect MRAC can stabilize the plant and force XT to follow XMT? Right? So if we recall our day 2 basics, first of all we can see whether we would like to see if this is a good model or not, right? If it's a good reference model or not. So you can see that R of t is given to be a bounded reference signal, and in fact for this question R is equal to 2, which is a good thing, right? Because let's just go to the basics first. Basics, Day2, right? Yeah. Yes. So in this MRAC lecture last time, we just saw that given a plant model and a reference model, we want the AM to be less than 0. Okay. And why? Because this means that then for a bounded input, you would get a bounded output, and given the structure with R being L, belonging to L infinity, that means R being a bounded signal, your state would also be bounded. That means your model state, which is XM, would be bounded. So it's a good model to follow, right? In that case, you would want your X to track XM. So your AM is less than 0 and R belongs to L infinity. And if we go to the question here, we see the same thing, right? That, where was it? Yeah. That here R is equal to 2, okay? For all t, that means it's bounded, it belongs to L infinity. And we have this, for this transfer function representation of the reference model, we have s plus 1 in the denominator. That means your pole is equal to -1. And if it's -1, it's in the left half plane. So that means it would lead you to a stable scenario. In fact, if you write it down in the time domain representation using the state space form, you would see that your AM turns out to be a negative parameter, okay? So given RT equal to 2 for all t, right, we will have to design an indirect MRAC. Which of the following indirect MRAC can stabilize? Now, what is basically meant by an indirect MRAC? If we again go back to the basics, we can see that in MRAC, we basically wanted our plant to follow the model state, right? We have a model reference and we were trying to learn the parameters because we don't know the system parameters, and accordingly design an adaptive controller. Now, in case of direct MRAC, we are not interested to know about the system parameters. We just want to design a suitable controller. So we simply go ahead with designing adaptation laws for this kx hat and kr hat, right? But in case of indirect, we are referring to the situations where now we want to learn about the unknown system parameters as well. So here kx hat is in fact equal to this expression itself, but instead of kx hat, we want to particularly learn about a hat and b hat, right? So that means these parameters a and b are learned, and that's why we call it indirect, because we are now first computing these estimates and then finding out what would be the value of this very gain here. Similarly, we are finding b hat and then seeing what would be the value of bm by b hat. So if we move back to that lecture, okay, so I think, yeah, you guys can see the lecture notes on your own, but I will just be continuing here with indirect MRAC. So we are given a plant model, which is x is equal to b by s minus 2 into u. Now, if I do multiplication here, then we have sx minus 2x is equal to bu. And if you take the inverse Laplace transform, we have x dot of t to be equal to 2, so I'm just doing a side change here, we have 2x of t plus but, right? It's like, so I do this side change and then I get x dot of t is equal to 2xt plus but, or if I just remove this t notations here, I can say that, well, x dot is equal to 2x plus bu. This is my plant. Okay. Now, what about the reference model? I was given that xm is equal to 2 by s plus 1 into r. So again, we do this side changing thing. We have s xm plus xm to be equal to 2r, right? And then if you do the same, inversion thing, inverse Laplace transform, you get xm dot t plus xm of t is equal to twice r of t. You do a side change, you'll end up with xm dot t is equal to minus xmt plus twice rt. Now, interestingly, like we had noticed earlier as well, the left half, the pole was in the left half plane, which made this model a good enough model to be followed, right? And you can see here as well, we have this minus xm. So I've just replaced this r to be equal to 2 here because it was given in the question. So you have this xm dot to be equal to minus xm plus 4, and if it's minus xm, if you recall what the reference model was explained in the class to be, we have this amxm plus r, right? Say bmr. Where we wanted this am to be less than 0. So here your am is equal to minus 1, which is less than 0, and that's good for us. So then what would be the error in tracking? So error is equal to e, error is denoted with e, which is equal to x minus xm. This is how we are defining it. Of course, you can say that e is equal to xm minus x. In that case, your analysis would just be slightly different with the symbols, that's it. So then your e dot, if you differentiate it, you get e dot to be equal to x dot minus xm dot, right? And now if you replace the dynamics, you have this 2x plus bu minus, instead of xm dot, we have this minus xm plus 4, right? So this is quite simple. Now you just write 2x plus bu plus xm minus 4, and then you have see, you have to learn the parameter b, right? So we bring this extra term, we just say that, well, this is equal to 2x plus bu plus xm minus 4, but now we are adding this term and subtracting this term as well. So basically this is the part using which we will carry on the analysis and come up with a law for b hat. So now we have 2x plus b hat u, right? I will just arranging the terms here. We have this 2x here, this b hat u is coming on this side, xm is here, right? Minus 4 is here, and this bu minus b hat u is written as b minus b hat u. Okay, so now you have 2x plus b hat u plus xm minus 4 plus, I'm just calling this b minus b hat to be b tilde. This is the error in learning the parameter b, right? This is the true value and b hat is the estimate, so b tilde is the error in learning b. Now, well, I have no idea why I wrote it. Yeah, so we had this e to be equal to x minus xm, and then your minus e would be equal to, well, of course, xm minus x, right? And you want to do something so that your e dot dynamics has something to do, with a minus e or a minus something of e, right? So the very first thing that we notice is that we have an xm here, right? So if we had something like 5xm, we could have designed for something like minus 5x and then added a plus 5x, so that we could land up with minus 5x minus xm, say plus 5x. This is just an example that I'm talking about. And so then this would be minus 5b plus 5x, say plus some other terms based on however you design, right? So if your e dot is equal to minus 5b, that's good, because now your error would be converging exponentially to some bounded state based on whichever terms are there inside these dotted parts, right? Now you're given that we have the simply xm. So that means you want to do something that so that you can bring an x here, a minus x here, and if you can bring a minus x, that would do your job, because now you would have minus of x plus xm, right? You would have minus of x plus xm, which is basically minus E, right? Whatever is the term here, we don't care about that right now. So the first objective is that I want to bring a minus x somehow. Okay, so let's see how we can do it. Yeah, so how do we want the expression is the same thing that I just discussed. How do we want to express, how do we want the expression of E dot to be? We want E dot to be equal to minus some positive quantity into E plus some other term. So in order to bring minus x here, what we do is, we had a 2x, right? You can see this expression, we had a 2x here. So we just write it as minus x plus 3x. It's a very simple thing to do. We just write minus x plus 3x, and then we keep the remaining expression same, plus xm minus 4 plus b tilde u. So we have plus xm minus 4. Did I just bring an extra term here? Yeah. So this b hat u, we have written it here, and then plus b tilde u. It's plus b tilde u. So then this is equal to minus, this is simply minus of x minus xm. What you are doing is you are bringing this term here, right? And then this 3x you are taking here. So you have minus x minus xm plus b hat u minus 4 minus 3x plus b tilde u. Now you can see that we have this u thing here, and we would like to do some design such that these terms can get neglected or can get cancelled. If this get cancelled, then it's easier for us, because we would be only left with E dot equal to minus E plus B tilde U if we can cancel the highlighted terms. So now I need to highlight them first. Yeah. If we can cancel this, then basically we would be left with E dot equal to minus E plus B tilde U, which is good for us. How? Let's just see that. So with U equal to, if you want B hat U minus 4 minus 3x to be equal to 0, this is simply saying that, well, you want U to be equal to 1 by B hat into 4 minus 3x with B hat not equal to 0. Of course, if it's equal to 0, then this would shoot up infinitely, and you don't want that. That might even lead to parameter drifts, which was one of the prime motivations for robustifying an adaptive law. So with U equal to 1 by B hat 4 minus 3x, what do we get? We get this to be minus E plus B tilde U, right? So now if we take V to be equal to the Lyapunov function candidate to be equal to half E square plus half B tilde square, because we will be designing a learning law for B hat as well, and you want your B tilde to be going to 0, right? Just like we considered here E, because we want x to follow xm, which means x minus xm to be 0, which means E to be going to 0. Similarly, we want B hat to follow B, right? It should be as close as possible to B. In other words, B tilde should then be as close as possible to 0. So when I'm doing the stability analysis with respect to origin, now my origin is for E and B tilde, because I want these two errors to be going to 0. So we take this V, Lyapunov function candidate, to be half E square plus half B tilde square. And then your V dot is equal to E into E dot plus B tilde into B tilde dot. Now you just replace the expression of E dot, which is minus E plus B tilde U. So you get E into minus E plus B tilde U, and then plus B tilde into B tilde dot. We still keep it in the same way, right? Because we are yet to design an adaptive law for it. You just expand it, you get minus E square plus B tilde E into U plus B tilde into B tilde dot. And then this is equal to, if you notice, we have this B tilde dot here. Now what is B tilde dot? It is basically, I can just add a line in front. You can write this to be minus E square plus B tilde EU plus b tilde, this b tilde dot, what is this? This is db tilde dt, right? Now what is b tilde? B tilde is equal to b minus b hat, which we had, I think, defined here, right? B minus b hat was written as b tilde. So we put b minus b hat here, and then we are left with now minus e square plus b tilde u minus b tilde n2. Now this is interesting. If you notice, we have minus e square plus b tilde eu plus b tilde. See, db dt would be 0, right? Because b is a constant parameter and it's not varying. And now you have only db hat dt, right? So this goes to 0, and this is simply equal to your b hat dot. So we just have now, instead of this plus b tilde and minus, we have minus b tilde into b hat dot, right? Now this is interesting. We wanted something negative definite or negative semi-definite at least, right? And then maybe we can go on with LaSalle to see how it can be carried forward. I think it's a non-autonomous system. Yeah, it's an unknown constant. So you can go on with LaSalle's invariance principle analysis to come up with the remaining stability analysis. But at least what we want is that this should be at least negative semi-definite. So you see that with B, wait, that's a mistake I did. With B hat dot to be equal to A into U, your V dot becomes minus E square, right? V dot becomes minus E square plus B tilde EU minus B tilde into B hat dot is now UE or EU. You can write either since it's a scalar case. And then these two get cancelled. You are left with only minus E square, which is less than equal to 0. And you can of course do the LaSalle's invariance principles analysis and then come up with an idea of what happens to this convergence scenario, right? So if we look into the options, I think it was one of the options. Yeah, what was our u? In this case, we took u to be 1 by b hat into 4 minus 3x. We get u to be, yeah, 1 by b hat into 4 minus 3x and 3x with b hat not equal to 0 and with b hat equal to u into e, right? B hat dot is equal to ue. So this turns out to be one of the correct options. Now you can actually do the remaining analysis on your own. You can pick a different u out of the options that were given to you, and then you can see with the other 3 points about what happens to the error and what how does your b hat go towards b, whether it converges or not. Okay, so I will leave the remaining part to you. I think, yeah, this is kind of a tough question and it would require you some time. Yeah, this is better, right? So what's the question? It says that consider the plant x dot equal to ax plus bu with b not equal to 0 and a is an unknown constant, and in fact signum of b is known for this given controller u, which is k1 hat into x minus sine t plus k2 hat into sine t plus k3 hat into cos t. Now which of the following represents the adaptive laws for k1 hat, k2 hat and k3 hat such that x of t will track sine t, right? So if we first look into this system, we have said that the plant is x dot equal to ax plus bu, a is unknown constant, b is an unknown constant, b is not equal to 0 and signum of b is known. right? So if b is not equal to 0 and signum of b is known, let us just see, recall quickly what the signum of b function meant. So basically, say if this is your b, signum of b simply says that if b is positive, it would take the value 1. If b is negative, signum of b would take the value -1, and if it's a 0, it would be 0. But of course, in our case, b is not equal to 0 is given already, right? Yeah. So we have this expression given to us. U is equal to k1 hat into x minus sine t plus k2 hat into sine t plus k3 hat into cos t. And it's desired that x tracks the reference signal sine of t, right? So the first idea that we get here, that see x of t, which is my desired signal, that is equal to sine t, and this is simply a command signal that I want my state to track, right? And further, no other reference model is given to us, right? So it's not a straightforward MRAC case anymore. What this is a simple adaptive command tracking problem, which was discussed in the last lecture for week 3, right? Or in the second lecture for week 3. So if x tracks sine t, sine t is your desired signal, and this is the command signal. So it's an adaptive command tracking problem. And we basically need to design laws for k1 hat dot, k2 hat dot, k3 hat dot, right? So if you also further notice something, or maybe we can discuss it later, but we'll first see what, we'll quickly give a brush up on this adaptive command tracking scenario. So what we mean by adaptive command tracking is that simply, again, adaptive law design, where the objective is that you want to track, you want your state to track a reference trajectory without any reference model being given to you. You are just given a simple signal, right? For example, if you consider this mechanical example of a robotic manipulator, it's just a hand is like a pick and place, suppose, say, or is simply a robotic manipulator, a hand, and you want this manipulator head to go from this star to this hash position following this very line. So this is your desired command signal, right? And you want it to track this very signal that has been given to this manipulator system. So for the simple case of LTI plants, we can consider this plant x dot to be equal to ax plus bu, and here AB is stabilizable, is assumed to be stabilizable. So you want to design ut such that x of t tracks xd of t, and of course we are assuming, like in case of the MRAC scenario, we just assume that the reference model had a nice behavior. That means it was a bounded input, bounded output system, and of course the reference signal belonged to L infinity. So similarly, now we assume that the desired trajectory and along with that is derivative, both are belonging to L infinity. That means both are bounded signals. So if we want to look into this tracking problem, we have a tracking error that's defined as x minus xt, right? And now we just want this to go to 0. So let's see what is E dot. E dot is equal to ax plus bu minus xt dot, which is equal to then ax plus bu. Now we keep the same thing, minus xt dot, but what we do is we add and subtract an extra term, which is amxt, right? So here, if you recall, similar to the case of MRAC, we introduce this am thing so that am is Hurwitz and it's user defined, of course, so that we can get some nice properties and ensure that E dot is converging to 0 at least, okay, or is at least going near to 0. So we design U is just picked up in the structure to be k1 into x plus k2 into xd plus k3 into xd dot, so that we can address both x, xd dot as well as xd. Okay, that's how the controller is designed. So if we replace this in the E dot expression, we get E dot to be equal to ax plus b k1x plus b k2 into xd plus b k3 into xd dot, and then you have the same term minus xd dot plus amxd minus amxd, right? So this is equal to basically a plus b into k1 into x, right? Plus you can see I'm bringing this term b k3 into xd dot I'm bringing this bk3 xt dot term here and minus xt dot here, right? And then we have this amxt and the minus amxt, and then at last I put this bk2 xt term. Okay, so turns out that provided the following assumption which I'm going to talk about, if is satisfied, then we get a nice enough tracking error. So assume that there exists, so this symbol means there exists. Let me just write it. This means there exists. So assume there exists such gains k1, k2, k3 such that a plus bk1 is equal to am, right? bk3 is equal to I and bk2 is equal to minus am. In that case, what happens? You can see if E dot is equal to a plus bk3 bk1x, I'm writing the same expression here, whichever was present, okay, plus bk3 minus I into xd dot minus amxt plus amxt plus bk2 into xd, right? So if a plus bk1 is equal to am, then in place of this very structure I'll be writing am, okay, and bk3 minus I, this would be cancelled because bk3 is taken to be equal to I, and here we have bk2 to be equal to minus am, so this two terms would also be cancelled, right? So you are left with amx and minus amxt, and then if you take this am thing common, then we have x minus xt. Now what was x minus xt? If we go back, that was our tracking error, right? So this is the tracking error part. So we have E dot to be equal to now AME. And if you remember, AM was chosen to be Hurwitz. So if it's Hurwitz, this is really good for us because now we can do Lyapunov analysis, and of course it would be converging to 0. So this means there is a scope to make X track XT, right? But what's the problem here? The problem is that we design this K1, K2, K3 assuming that we have the knowledge of A and B, right? But in practice, we do not have the knowledge. We do not know what A and B is, and that's why we go for this adaptive, parameter learning laws. So instead of this, since we can't implement it directly, we consider the certainty equivalence controller, which is the same thing except that now we will put the hats. That means we will put the estimates. So U is equal to now consider to be K1 hat X plus K2 hat into XD plus K3 hat into XD dot, right? If you look into the previous controller, we have just replaced this K1, K2, K3 by their hats. That's it. So then you can find E dot. You do the same replacement, okay? And if you find E dot, you will obtain an expression in terms of K1 tilde, K2 tilde and K3 tilde. Why? Because we are still assuming that these conditions are satisfied. So you can use this condition and then find E dot's expression. And once you do that, it becomes very easy. You can use similar steps as shown in MRAC design to come up with the adaptive laws. Okay. So we will use the same idea here, but it's this design is slightly different. So I'll just give you the hint so that you can at least go till the Lyapunov analysis part. if you notice, we have the same structure here, right? Where is the page? You can see we have the same structure. We want to track sine of t. That means your sine of t is your xt, isn't it? So if sine of t is your xt, we have something like something into some k1 hat into x minus xt plus k2 hat into xt plus k3 hat into xt dot, because it's just sine t's derivative, which is cosine of t, right? So the expression that we obtain here is similar to what we saw for the adaptive command tracking design. The only difference is that earlier you had k1 hat into x, now you have k1 hat into x minus xt, and that brings a small tweaking that is required in the Lyapunov analysis before you reach the Lyapunov analysis. So let's look into that. We need to design laws for k1 hat dot, k2 hat dot, and k3 hat dot. The system is given x dot equal to ax plus bu. I think, yeah, did I write it correctly? Yeah. So the plant is x dot equal to ax plus bu, b is not equal to 0, xt is sine t, xt dot is cosine of t, and our assumption is therefore satisfied that xt and xt dot are both bounded. Right. So the tracking error is x minus xt, and if we find e dot, which is equal to x dot minus xt dot, now you replace x dot, you get ax plus bu minus cos of t. Or see, this is the catch that I would like to just analyze here. Earlier what we did was, we had, if we follow as shown in the class, what we have is ax plus bu minus cosine of t, and then the analysis tells you that, well, you should proceed with some am, that is Hurwitz, or since it's a scalar case, am that is negative, and you write amxt minus amxt. Okay, this is as per the discussion that was just made, okay, where am is less than 0, right? This is what we should have done. Only it turns out that I would leave it to you. You guys can continue the analysis with this as well, and you can at least see what happens, or in case you can come up with a different controller that works, or a different Lyapunov function, because Lyapunov functions are not unique. Okay, there's a variety of Lyapunov functions that might work for the same problem, and so accordingly you might come up with a different controller as well, which is not theoretically wrong at all. Okay, so since we are given some options in this question, what we will do is, we will discard this idea and we will do some other tweaking. What we will do is, we will have a plus a minus a instead of this am and minus am. Now, of course, we do not know what a is, right? But this is just for analysis. We are not using this a in any input. So we have this ax plus bu minus cosine of t plus a sine of t minus a sine of t. And now if you see, I have here ax and I have here minus a sine t, right? And so this lead me to a into e, because x minus sine t was my e, right? And then we have the remaining terms, which is fine, plus bu minus cos t plus a sine t. Now, why did we do this change? What could have been the motivation? Just a moment. Yeah, what could have been the motivation for bringing a instead of am? If we go back to the controller that was given to us in the lecture, we had this to be u equal to k1 hat into x. Only x was there, not x minus sine of t. What is this x minus sine t? This is e again, right? So we can simply say that, well, this is equal to k1 hat e plus k2 hat xt plus k3 hat xt dot. Right? It's the same thing. So in class we had here x, but now we have here e. So that's why since u is written in if something in form of E, the something as an expression of E. That's why in order to bring the same E again, we do the analysis here. We start the analysis here with A instead of AM, so that we can take this A common and come up with an AE expression here. Now that we have this AE, you see our input can be designed to be minus AE, 1 by B minus AE, plus cos t, so that these are cancelled, minus A sin t, so that these two are also cancelled, right? I hope it's clear. Yeah. In order to cancel this, we have this very term. In order to cancel this, we have this term. And in order to cancel this plus A sin t, we have this other term here. Okay. Now the problem is that, well, then E dot would become equal to 0, right? But that's not what we want. We want it to E dot is equal to 0 means E would just stay constant, so the error would not change. Basically there is no tracking, right? That's not what we want. So what we do is that we introduce another signal, which is 1 by B AME in this position now, because that was our prime motive anyways, right? That we wanted E dot to be equal to some AM into E, with AM being less than 0. That's what we wanted anyways. So to ensure that we get this expression again, we bring a 1 by B AME, and this AM is now Hurwitz, is less than 0 by a user's choice. So we have this E dot equal to AME now. Okay, if you place this controller expression, we will get this. However, like we just discussed, we do not know the values of A and B, right? So if we do not know the values of A and B, we can at least say that the matching conditions are satisfied. What are the matching conditions? Well, AM minus A by B should be your K1, minus A by B would be your K2, 1 by B would be your K3, right? So you can use this matching conditions now, which is an assumption that there exists such K1, K2, K3 which satisfies these conditions. And of course you don't have to worry about B, because the question I think already said that B is not equal to 0. Yeah, B is not equal to 0. So you see we have something like K1 hat into this E plus K2 hat into xt plus K3 hat into xt dot. You can again match it if you want. See, it's the same expression. So now this is your K1, minus A by B is your K2, 1 by B is your K3. Now since you do not know this, what would be the certainty equivalence controller? It would be the same thing, except now we will have the hats here. Okay, and if you have the hats here, you can simply replace this input into the E dot expression, and then use this matching conditions to come up with this expression. You have AME minus B K1 tilde E minus B K2 tilde sin t minus B K3 tilde cos t. And here this, let me just write it down for the sake of completeness. K1 tilde is simply K1 minus K1 hat okay. So you use the matching conditions and put this U expression in E dots expression, and use the matching, let me just write it, and use the matching conditions to obtain this E dot. Okay, and then you simply pick V, which is a Lyapunov function, which should be a function of E, K1 tilde, K2 tilde and K3 tilde, because now you want all these errors to go to 0, to be half E square plus mod of P by 2 into K1 tilde square plus mod of P by 2 into K2 tilde square plus mod of P by 2 into K3 tilde square. Okay. So with this, if you carry on the analysis, you can find V dot. This is a positive definite function of V. And so V is a positive definite function, and if you find V dot, I think I will just leave it to you. Do the differentiation, right? And then simply you have to cancel some terms. So you design k1 hat dot, k2 hat dot, k3 hat dot accordingly so that those terms get cancelled, and then you can easily pick out of the options that were given to you. You see, these are the options. So keep this in mind that you have to find expressions for the hats, not for the tildes. Okay. So basically, when you do the differentiation here, let me just show it to you quickly. When you do the differentiations here, you will have for v dot, you will have something of k1 tilde dot, k2 tilde dot, k3 tilde dot. But notice that k1 tilde dot is equal to d dt of k1 minus k1 hat. So this is equal to minus k1 hat dot. Then you have k2 tilde dot to be equal to minus k2 hat dot. K3 tilde dot is equal to minus k3 hat dot. Okay. So sorry, I just wrote somewhere and it didn't appear. Yeah. So this is the scenario. You use these cases and then appropriately find the adaptation loss for k1 hat dot, k2 hat dot, and k3 hat dot. Okay. So are there any doubts? This was a long question, so let me know if there are any doubts, or I'll just move on to the next two questions. Okay, so we'll go on with the next question. It says that let x1, x2 are system states, and delta 1 of x1, x2 and delta 2 of x1, x2. These are some uncertain terms. Then which of the following represents a system with matched uncertainty, right? And I think this is quite easy to follow, provided you know what is a matched uncertainty. So we will quickly go through the basics and then come back to the question. So I think this was explained in the class as well, that given say a function, given a dynamics, okay, x dot equal to f of x plus g of x into u plus g of x into delta. So here delta is some uncertainty that is not known to us. So note here that we can write it as f of x plus g of x into u plus delta, right? And this delta, if it lies in the span of u, so you can just basically say that, well, you can account for the uncertainty delta. How? You can simply write that, well, let u be equal to minus of delta, right? But since you do not know delta, what you will say is that let u be equal to minus of delta hat, and then you will do you will design an estimation law for delta hat. Okay, so you can account for the uncertainty delta. That means delta here is a matched uncertainty. Why is it matched? Because you could match it with something to cancel its effect, right? So if we take an example, we had given say x1 dot equal to x2 and x2 dot equal to 1 plus x2 square into u plus e to the power x1 x2 into delta. Okay. Now see, you can simply write that u is equal to minus e into x1 x2 to the power x1 x2 into delta hat divided by 1 plus x2 square, and then plus some other terms, whatever is required. Okay, so then by writing this, you can try and cancel the effect of delta here. And also note that we have this 1 plus x2 square here, so even if you divide it, it would always be positive, so there is no chance of u being unbounded, at least for this term, right? So this here is a matched uncertainty. Now let us consider another example. Say x1 dot is equal to x2 plus x1 square delta, and x2 dot is equal to 1 plus x2 square into u plus e to the power x1 x2 into delta. Now again, u here can be written in this form, right? Plus say some other terms. you can have plus some other terms here. Right? So this can then cancel the effect of delta in x2 dot dynamics. However, notice no matter what you design, what you design, you can't cancel the effect of delta in x1 dot, right? So this part cannot be addressed. You cannot do anything to handle this. Okay, so this here is an unmatched uncertainty, right? Because this delta does not lie in the span of you, this very delta. Okay, so if we look into this question now, I think it's easy to follow. Yeah, so we understand now what is a matched uncertainty. Let us pick up each of these examples. So can we handle the uncertainties using the input u? That's what we have to see to know whether it's a matched uncertainty or not. So the first system was x1 dot is equal to x2 and x2 dot is equal to x1 plus delta 1 plus u. So it's very easy. You can just write u to be equal to minus delta 1 hat plus some other terms if you require, and this would lead to a cancellation here, right? It's like you will have something like delta 1 tilde, and if you have a delta 1 tilde, you can have a suitable adaptation law for it, which can try and negate the effect of delta 1 overall. So this is a matched uncertainty example. What about the next one? We have x1 dot is equal to x1 plus delta 1 plus u, and then x2 dot is equal to x1 x2. So I think the example is just the indices are given in the opposite way, simply to confuse you all, that's it. So if you sort it down and write it in the proper form, state space form, then you see that u can be again written as minus delta 1 hat plus something, which is a matched uncertainty case. What about this? I think is very clear now, because you can design u to be anything, but it will never come and affect delta 1 directly, right? So if it cannot affect delta 1 directly, basically this is an unmatched case. So yeah, the question is overall easy, it's not that difficult. And so we'll now move on to the last question. Indirect MRAC is preferred if knowledge of the system parameters are required. Is it true or false? Right? So that means when do you do indirect MRAC? And if we look at the basics of day 2, we had this direct MRAC structure and indirect MRAC structure. Indirect MRAC, we simply find the gains involved with the state and reference signal in order to obtain the input u, right? But in case of indirect MRAC, we do not compute kx hat and kr hat directly. We just go for finding the expressions of a hat and b hat, and then we use this formula to come up with the expression of kx hat and kr hat. Right? That's why it's called indirect. So what's the motivation for doing this? Of course, is because we want to learn the system parameters and not only the gains related to the input. So if we look at this question, indirect MRAC is preferred if knowledge of the system parameters are required. I think which means a hat and b hat are required, and I think that would give you the answer very easily. Okay. Yeah, so that's it. I will be stopping the session here today. If you have any questions, you can let me know. So yeah, so you guys can stay only if you have doubts, otherwise you can leave. I'll also end the session within the next 20 minutes. So it's up to you. If there are no doubts, you can leave. That's it.
Yeah, thank you.
Okay, thank you.
Okay. So I think I will just stop the session here, and yeah, we will meet again next Tuesday to discuss about the assignment for solutions, right? So yeah, I will stop the meeting here. Okay. Have a nice week. Bye.